So, we are still talking about derivatives that we have been dealing with for quite some time now. We spent all last week on it and a little bit even the week before, so we know derivatives have lots of different applications. It is the slope of a tangent line, it is the instantaneous velocity, it is the derivative is another name, we call it f prime. And so we are going to continue to learn what these things can all represent. We know a few things so far though, and we're going to kind of make some generalizations here. We know that a constant is just y equals a number. Y equals 4, y equals 6, that's a horizontal line. Okay, that's called a constant function. What is the slope of a horizontal line? 0. And the derivative is the slope of the tangent line. So the slope of the tangent line here is always going to be 0. So we've seen it come up a few times, mainly when we are doing those higher derivatives. We know we do the first, second, third derivative, and at some point we were getting 0 for an answer. So it is now true that the derivative of a constant is 0. We could prove it. I don't do the actual math proofs for you very often, but this is a pretty simple one. So if you have a function that is equal to a constant, the derivative, its limit is h approaches 0, f of x plus h, which is just c here, because there's nowhere to plug it in, minus f of x, which is also c, over h, and we get 0 for our answer. So from this point forward, you no longer have to work that out. It is now assumed. So anytime you have the derivative of a constant, you can just tell me it is 0. You do not have to prove it or do the whole definition to get that. Alright, so let's see if we can kind of generalize this to come up with some others that we could maybe know the derivative and not have to work it out every time. So let's talk about power functions when you have x to a power. If it's just x to the first, what's the slope of this line? Y equals x just has a slope of 1. So that means the derivative of x is 1. Okay. Let's think about if it's 2. So our function is x squared. Then our derivative, f of x plus h, minus f of x over h What happens? So we're taking h out of what's left. You can drop those h's. If you plug in your 0 then, you get 2x. So here's what we have so far. Here's my derivative, or my function, and there's the derivative. We know that if the function is x, the derivative is 1. If the function is x squared, the derivative is 2x. Let's work out some more. If it's 3, so the limit h approaches 0, f of x plus h minus f of x over h. So x plus h cubed, you could multiply it out 3 times. You could use that shortcut trick we talked about last week. Do you guys remember that, the little pyramid? So it would be a 1x cubed, a 3x squared h, a 3x h squared, and h cubed. What happens now? Take out an h. So now those h's cancel. So you plug in a 0 for all the remaining h's. You get 3x squared. So, we've got the derivative of x cubed is 3x squared. Does anyone have a prediction for the derivative of x to the 4th? Okay, let's see if you're right. So you guys know how I'm working these out so far? So if we did the 4th, so we have the limit h approaches 0, f of x plus h minus f of x over h. Okay, if you wanted to do the shortcut for x plus h to the 4th, so it'd be 1, 4, 6, 4, 1. So it's 1x to the 4th, a 4x cubed h, 6x squared h squared, a 4xh cubed, and a 1h cubed to the 4th. Do you guys understand how I got that? And you could, of course, multiply it all out. So now what happens? So if you cancel your h's, plug in your zeros, and we get, just like you predicted, a 4x cubed. So how did you know what that was going to be? What's the pattern you're seeing? Okay. Alright, so the exponent becomes the coefficient. And what happens to the power? It goes down 1. So if I said x to the 10th, what would that derivative be? And x to the 9th. You can see it worked with this one as well. This is a x to the 1st, so the 1 comes down. If you subtract 1 from the power, what's anything to the 0 power? 1. So, if you've been wondering how I could always look over your shoulders and tell you if you had the right derivative or not, it's because I was using this shortcut. Now, there's a reason I didn't just teach you this shortcut at the beginning, because this works for polynomials, but there's a whole lot more to it. That's why we're not going to be done with derivatives until like February. So there's a lot of rules for different things, but when we have just a single term like this, our derivative can be found by bringing down the exponent and subtracting 1 from the power. So we are going to get away from doing this entire definition every time we do a derivative. We're still going to say that because there will be some where we probably can't do this shortcut. You know, if I said 1 over x minus 5, I can't write that as x to a power. So I can't do this shortcut there. This doesn't always work. But when it can, we will use this to find our derivatives. All right, so let's do some derivatives without doing all the work. So my function is x to the 6th. So what is f prime of x? Exponent comes down, keep your x, subtract 1 from the power. So the derivative is 6x to the 5th. Alright, if you have x to the 1000th power, what is the derivative? 1000x to the 999. That would be one that we could not have done with the other rule. There would be no way, I mean, there would be, but we don't really have the time to do x plus h to the 1000th power. Okay, so that would have been extremely ugly to do before. Alright, if y equals 2 to the 4th, dy dt, just another notation for a derivative, would be d over dr of r cubed. I'm just using a lot of different notations here. All of these mean the derivative. So the derivative of r to the 3rd, r to the 2nd. So far, so good? So let's talk about if it's not written in this form. Now, my first goal is going to be to say, okay, is there any way I can write this as a number or a variable to a power? Because if I can get this to just be x to some power, then I can do my shortcut. If I can't, I have to do the whole limit definition to get my derivative. So if I said 1 over x squared, is there any way I could rewrite that? Remember, a radical would turn into a fraction. So the square root of x is x to the 1/2. When it's on the denominator, you can bring it back up by making it a negative power. So then my derivative, exponent comes down. And if you subtract 1 from your power, what is negative 2 minus 1? Derivative is negative 2x to the negative. You can leave it like that. If you had done it the long way, you probably would have ended with a fraction. Okay, these are equivalent. I do not care how you write those. B. If I said the cube root of x squared, how could I rewrite that? Derivative. Exponent comes down, so it's a 2/3 x. You subtract 1, so 2/3 minus 1. Okay, you are welcome to rewrite that with radicals and putting it on the denominator, but it is not necessary. You can just leave your answer like that for your derivative. Everything's okay? Something else I want to talk about today. We're going to keep doing derivatives, but I'm also going to mention the idea of a normal line. So a tangent line, if we are looking at a curve, okay, we know the tangent line is basically hits it and bounces off, right? The normal line is the line that is perpendicular to that. So if you do the line that would hit the tangent line and make a right angle, that is what's called the normal line. We don't use it nearly as much because it doesn't have as many applications as the tangent line does, but we do see it occasionally, so it is something that we need to talk about. And I think the next slide on there, I did give you the definition as well. So the picture is probably a little more obvious, but the definition just says the normal line at a point is the line that is perpendicular to the tangent line. So if I'm asking you to write an equation for a normal line, you're still going to have to do the derivative to get the slope of a tangent line. And then how are perpendicular lines? What's true about their slopes? Opposite reciprocals. We flip it and change the sign. So let's try one. I want the equation of the tangent line and normal line to the curve f of x equals this x radical x at the point 1, 1. So, first, no matter what, I have to get the derivative. We can do it the long way, but if I can figure out how to write this as x to a power, I can do the shortcut. So we have x, this is times the square root of x. That's x to what power? 1/2. If you're multiplying those, what do you do with the exponents? So 1 plus 1/2 is 3/2. So that is x to the 3/2 power. So my derivative, exponent comes down, keep your x, subtract 1 from the power, so 3/2 minus 1 is 1/2. Or if you preferred, you could write this as 3/2 times the square root of x. So now, we have to write the equation of the tangent line. To write the equation of a line, you need a point and a slope. My derivative is my equation for the slope. So my x was 1. So we get 3/2 to the slope. Everybody okay with that part? And so now the equation of the line, we have the slope is 3/2, the point is 1, 1, so plug into y equals mx plus b. So our actual line is y equals 3/2 x minus 1. And then I ask for the equation of the normal line. The normal line is perpendicular to it. So if the tangent line had a slope of 3/2, what's the slope of the tangent line? And it's still the same point, 1, 1. So plug in y equals mx plus b. So we get negative 2/3 x plus 5x. Questions here? Let's do another one. So if I want the equation of the normal line to the curve f of x equals x to the 4th at the point negative 2, 16. So to write the equation of a line, we need a point and a slope. I've given you the point, we need to get the slope of that normal line. What will I have to do first? We need to get the slope of the tangent line. How do we do that? Derivative. What is the derivative of x to the 4th? So for my tangent line, my slope would be 4 times negative 2 cubed. So negative 8 times 4 is negative 32. So for the normal line, what would be our slope? 1 over positive 32. Flip it and change the sign. And then we know our point is -2, 16. Y equals m times x plus b. 16 over 1, so that would be 256 over 16 plus 1. So the final equation of that normal line is 1 over 32x is 257 over 16. Any questions on that? So I want to hit just a few more rules so far. I'm probably going to skip the proofs on these unless you guys really want to see them. I'm happy to show it if anyone's interested. They all go back to that limit definition. The first one is the constant multiple rule. If you have something times a function, then that coefficient is basically just going to trail along. Probably the easiest way to think about it is if I had something like f of x equals 7x to the 12th power. Okay, and I wanted to do the derivative. That 7 is just a coefficient, so you basically do 7 times the derivative of x to the 12th. What's the derivative of x to the 12th? And so then you can multiply the 7 and the 12 and you get 84x to the 11th. So it's saying we can still do the derivative if we have a coefficient. It's just going to be multiplied with our derivative. Do you guys want to see the proof to that, or do you care? Do you believe me? You don't think I'm lying to you? You guys are so trusting. So why don't you guys try a couple? Take a second and see if you can figure out the derivative of each of these, and then we'll check and see how you did. So the first one, 3 times derivative of x to the 4th would be 4x cubed. So 12x to the 3rd. Second one, that negative, it's just like having a negative 1. What is the derivative of x? 1. If you forget it, you can always work it out. The 1 comes down. X, if you subtract 1 from the power, it's 0. Anything to the 0 power is 1. So we just get a negative 1 there. The negative just slipped. Is that okay? The next two rules are going to allow us to extend this into polynomials. It tells us that if you have differentiable functions, you can do each of their derivatives separately. So if I had the derivative of something plus something, you do the derivative of the first plus the derivative of the second. So in a polynomial, we can do the derivative of each individual term. You guys want to see the proof, or do you believe me? Good. Believe me. The same is true with subtracting. So it doesn't matter adding or subtracting, you can do individual terms. But something important to note, it does not work this way for multiplication and division. Okay, so when we have a fraction, we can't just do derivative at the top and derivative at the bottom. We will get to how to do that, but for now, this only works for addition and subtraction. So if I asked you to find the derivative of this huge thing, probably would have taken you the entire class period to do that problem on Friday if you had to do the whole limit definition. But now, we know we can just do the derivative of each individual term. So the derivative of x to the 8th would be x to the 7th. Plus the derivative of 12x to the 5th. So when you bring that 5 down, you have to multiply it with the 12. So 5 times 12 will be 60. X, if you subtract 1 from the power, it's now to the 4th. Minus 4x to the 4th. So if you bring down your exponent, 4 times 4 is 16. X, subtract 1 from the power, cubed. Plus 3 times 10 gives me a 30. X squared. Minus, what's the derivative of 6x? 6. Plus, what's the derivative of 5? The derivative of a constant? 0. So you could put that plus 0, but really we don't need it, so we'll just leave it off. So there is my derivative. Why don't we stop there for today? So homework-wise, you guys are ready to do this chunk. 3 through 17, odd, 23, and 29.